Okay, so let me go back on the demo and make new script and the finite difference. Well, we said that we are going to be using an ODE solver, right? To use the ODE solver, we have to write a function. Function du dt is equal to, let's say, oh, by the way, the equation we are solving is called the advection equation, okay? And the ODE solver, for example, ODE 45 would take a time and a u, okay? And actually, we are the discretization doesn't depend on time at all, so we can just say it's tilde. So MATLAB is not going to bother us with warnings, and it's known to MATLAB by its name. Oh, okay, that's fine. We are going to be using this as a function in a script. All right. So here, our u is not a number anymore. It's a collection of numbers, one on each grid point. All right. And to basically reproduce what we saw on the analytical solution, let's actually also assume a periodic boundary condition. Okay, so basically u at the right-hand side is equal to u at the left-hand side, so that we actually keep track of one less number. So let's forget about u at the very end. It is equal to u at the very beginning. Okay. So which scheme do we want to implement first? Let's implement the first order scheme first. All right. So to implement the first order scheme, we need to figure out, okay, what is my u minus my u on my left-hand side? So if u is a vector, what is u on the left-hand side? Let's say ul is equal to, well, on the first grid point, my ul is what? My ul is u at end, right? Because of periodic boundary conditions, right? I'm at the very left. So if I have a bunch of grid points, and when I'm at the very left, my left neighbor is actually wraps around. It's the very last point I have here, right? So remember, this point is the same as this point. So this point to the left is the very end of the solution array. Got it? Okay. And then starting afterwards, it's u from 1 to n minus 1. Agreed? So this is a vectorized form of the solution at the previous grid point. Does it make sense? Okay, so du dx is going to be approximated by u minus ul divided by delta x. So we have to figure out what is delta x in this case. So imagine the entire, so let's actually solve this equation for domain from x in 0 and 1, okay? Then if we have a uniform spacing, my delta x is going to be 1 divided by the number of intervals. Okay, and in this case, if my last grid point is not kept track of, it's the same as the first grid point. The number of intervals is the same as the number of grid points I keep track of. So what I can say is that n is equal to the length of u, and dx is 1 over n. I don't remember if I need this. Then divided by dx, right? Okay. So now let's just to make it simple, let's say a is equal to 1. So I'm gonna say a is equal to 1. So that's the speed of the solution traveling towards the right, and du dt is equal to minus a times du dx, right? That's the PDE. That's what the PDE is. Du dt equal to minus a times du dx. Okay, so now we have basically completed our first example of finite difference, right? We are approximating the spatial derivative, and this is an implementation of an ordinary differential equation we can actually plug in into MATLAB's ODE solver. So let's do that. Initial solution. Let's actually, I think I have a draw periodic function here, right? That actually says that n and u name. Okay, so draw periodic function. Let's. How many grid points would you like? 100? 50? Okay. All right. And I have to give a name like initial condition. Okay.